Welcome to The Explainer. So today, we're going to talk about a massive global race to protect pretty much everything you do online. And what's at stake? Well, just every password, every private message, every single bank transaction, all of it is being threatened by a totally new kind of computer that's just over the horizon. We're going to break down exactly how the world is building a shield against it.
Okay, so to really get this, we've got to start with the problem itself. And honestly, it sounds a little bit like something straight out of science fiction, but I promise you, the danger is very, very real.
The short answer? Yeah, pretty much. I know, it sounds incredibly alarming, but a powerful enough quantum computer could literally unravel the very fabric of our digital security. And that is why the race is on to make sure that never, ever happens.
All right, so think about it like this. The computer or phone you're on right now, it thinks in bits. They're like simple light switches. They can be on or off, a 1 or a 0. That's it. Quantum computers, though, they work with something called qubits. Now, thanks to this wild property of quantum mechanics called superposition, a qubit can be a 0, a 1, or both at the same time. This ability to explore multiple possibilities at once doesn't just make them a little faster for certain problems, it makes them unimaginably more powerful.
So here's the kicker. The way we protect everything online right now is by using math problems that are just way too hard for our current computers to solve. A great example is trying to figure out which two massive prime numbers you multiply together to get an even more gigantic number. A classical computer would take, ages to figure that out. But a big quantum computer running a specific recipe, an algorithm from 1994 called Shor's algorithm, could just tear through that problem like it's nothing. It could basically find the secret keys to all our digital locks.
And this is where it gets kind of spooky. It leads to this strategy that people are calling harvest now, decrypt later. What that means is, right now, adversaries are sucking up huge amounts of encrypted data. We're talking private messages, corporate secrets, government communications, and they're just storing it. They're just sitting on it, waiting for the day they finally have a quantum computer powerful enough to unlock everything. So the theft is happening today, even if the damage comes years from now.
And this is where the timeline gets really uncomfortable. Most experts think a quantum computer capable of breaking our current encryption is maybe 10 to 15 years away. But switching the entire planet's digital infrastructure over to a new security standard, that could take 10 to 20 years. You see the mismatch there, right? We could literally run out of time. And that's why this work to build a defense had to start years ago.
So, okay, if our current digital locks are basically about to be picked, how do we build new ones? Well, that's where the solution comes in, an entirely new kind of digital shield.
The answer is something called Post-Quantum Cryptography, or PQC for short. And let's be super clear, these are not just, slightly stronger versions of our old encryption. They are completely new types of digital locks, built on totally different kinds of math problems that we're pretty sure are going to be hard for any computer to solve, whether it's classical or quantum.
And what's really smart is that the experts didn't just bet the farm on one new idea. They developed a whole bunch of them. You've got lattice-based crypto, which is kind of like trying to find your way through a crazy 1,000-dimensional maze. Then there's hash-based crypto, which relies on things that are easy to do but almost impossible to undo. Sort of like how it's easy to scramble an egg, but good luck trying to unscramble it. By having all these different approaches, we're not putting all our security eggs in one basket.
Okay, so creating these new locks is one thing, but how in the world do you get the entire planet to agree on which ones to actually use? I mean, that's a huge undertaking. So how's that being handled?
And this is the cool part. This wasn't some secret project cooked up in a basement. It was a totally open, transparent, global competition. It was led by the U.S. National Institute of Standards and Technology, or NIST, and they basically sent out a call to the entire world, saying, hey, send us your best, most quantum-proof ideas.
You can really think of it like a cryptographic Olympics. It started with 69 different candidates from all over the world. And for years, these algorithms were thrown into a public arena where all the smartest people in the field just tried their best to break them. They were attacked, they were stress-tested, and they were picked apart for any tiny weakness. Only the absolute toughest ones survived to become our new standards.
And just this year, in 2024, the first winners were officially announced. Now, I know names like ML-Chem and ML-DSA sound super technical, but just think of them as the new, standardized, ready-to-use toolkits for our digital world. One is for setting up a secure channel, and the other is for proving something is authentic. These are the absolute fundamental building blocks for a safer internet. All right, so we have our new quantum-proof shield. Now for the really hard part. How do you roll this out across the entire internet?
without, breaking everything in the process.
The trick is to use a really clever strategy called hybrid encryption. So instead of just ripping out the old lock and putting in a new one, systems will actually use both at the same time, a new PQC lock combined with one of the old, trusted ones. It means your data is protected by two different kinds of locks simultaneously. It's a fantastic safety net. If for some reason an unexpected flaw is found in the new lock, the old one is still there holding strong.
But, it's not quite as simple as just flipping a switch. One of the biggest engineering hurdles is just size. A classic encryption key might be a tiny 32 bytes, but one of our new champions, ML-Chem, is over 1,000 bytes. That is a massive difference, and all that extra data can slow things down if you're not careful. So engineers have to be really smart about how they implement all this.
And this is the best part. This isn't some far-off future thing. It's happening right now. Apple is already upgrading iMessage with a new PQC protocol. Google and Cloudflare are rolling this out in the Chrome browser and across their massive networks. The secure messaging app Signal is already using a quantum-resistant protocol. The upgrade, believe it or not, has already begun, silently behind the scenes.
Okay, this all sounds really huge and complicated, so let's bring it back home for a second. What does this massive global security upgrade actually mean for you?
So after all this, after hearing about quantum threats and cryptographic Olympics and hybrid encryption, you're probably asking a pretty simple question. Okay, so what do I need to do? And the answer, which is just fantastic, is absolutely nothing. This entire planet-wide upgrade is being designed to happen completely in the background. It's being handled by the engineers at Google and Apple, the people who build your apps and browsers, and the cryptographers who design the very backbone of the internet. The best security, after all, is the kind you never even have to think about. When you step back, this whole thing is pretty incredible. It's a powerful testament to our ability to see a crisis coming down the road and actually work together, globally, to solve it before it happens. We're building the shield before the arrows even start to fly. And it just leaves you with one final thought. As we secure our digital world against this quantum threat, what's the next big challenge that's just over the horizon? What's the next frontier we need to start protecting today?